All right, honors chemistry people, we are now going to start looking at the, we are going to start looking at the Vesper model today. And it looks like my print here has gone a little awry. So this here on the side should say Vesper. VSEPR. And this is the model that we are going to use to put on these Lewis structures that we started drawing yesterday. Now, remember when we look at drawing Lewis structures, there's a couple things that we need to do first. The very first thing we need to do is count up all the valence electrons and all the atoms that are in that molecule. And the second thing we need to do is figure out what atom is going to be in the middle. And then we draw a single bond to each of the rest of the atoms and that single atom. And then we try and satisfy every atom's octet or valence structure octet by putting in lone pairs or double or triple bonds until all the valence electrons that we had are used up. Okay, now we're going to put another layer on top of this. And we are now going to determine the geometries or the shapes of these molecules. And the geometries are determined by what we call the Vesper model. So Vesper, as you have probably surmised by now, Vesper stands for, it's an acronym. So let's look at what this Vesper stands for. V stands for valence. So we're looking at the valence electrons, and S is shell. So the valence shell electrons pair. Have you noticed that each orbital has a pair of electrons in it? Repulsion. Repulsion. Now remember, electrons are negatively charged. So if I have electrons next to an electron, they're going to pull apart. So what this Vesper model does is it helps us envision in three-dimensional space the geometries that will get those electrons, get the electrons as far away from each other as possible. So we're trying to get things as far away from each other as possible, okay? So this is just a really fancy way of meaning or showing that the electron pairs around that center atom are going to be as far away from each other as possible. So let's look at methane again. So if we look at methane, it's CH4. So carbon gives us 4 valence electrons. Hydrogen gives us 1 valence electron, but we've got 4 of them. So we're going to multiply that by 4. 4 plus 4 gives us 8 valence electrons. Now the next thing we've got to do is figure out what's going to be in the middle, right? Now we know that hydrogen can't be in the middle. So we're going to put carbon in the middle. We're going to put hydrogen single bonded all the way around. Now the next thing that we have to look at are all of these pairs of electrons on the center atom. Now that's what we're going to look at. We're going to look at the electrons on the center atom being carbon. So are they bonding electrons or are they non-bonding electrons? What I see here is I see 1, 2, 3, 4 pairs of bonding electrons. So all of them are bonding electrons. We have 4 bonding pairs of electrons. Okay, the next thing that we need to do now is to see where that takes us. So in a few pages, so on page, 150? No, not even 150. 148. 148 and page 149 in your book. If you want to go forward to look at these charts, I've got them on a different thing. So we said we have the number of electron dense areas. Let's look at this. If I look at the number of electron dense areas, I have 1, 2, 3, 4 areas of electron density around that center, and all 4 of them are bonding. So let's look at this chart. I have 4 areas of electron density, and all 4 of them are bonding. That means I have no lone pairs. So my electron pair geometry is going to be a tetrahedral shape. And we are going to also have a tetrahedral molecular geometry because none of those lone pairs we don't have any lone pairs to take up any space. So I will do kind of a help session with some Molly mods to help you look at this a little bit better. But this is the chart that you're going to look at to see what that shape is. Now, if you want some more information, I've got a chart on the next page that essentially does this. This is also the electron number of areas that are electron dense, I would say. How many are shared pairs? How many are lone pairs? This will give you hybridization, which is what you need to know in AP chemistry. We're not going to focus on AP chemistry stuff, but we will focus on the shape and we will focus on the bond angle. So let's do methane again. So if I look at methane, oh my gosh, let's minimize that. That doesn't want to minimize. Okay, so if I look at methane, we now have 4 total pairs around that center atom. We have 4 that are bonding or shared. So we will have a bond angle of 109.5 degrees, and we will have a shape that is tetrahedral. So this is how we figure out whether things are tetrahedral, trigonal planar, for example, if we have 3 bonding areas around there or not. We use these 2 charts right here to figure out our shapes and our angles. Okay, so let's go back to our notes here. So, how can these pairs arrange themselves around an atom so that they are as far apart away from each other? We looked up on that chart and we found it to be a tetrahedral arrangement. Okay, so it is a tetrahedral arrangement with the electron geometry. Because we've got 4 pairs of electrons around that center atom. Okay, and because all 4 of those pairs are all bonding, that means our molecular shape is also tetrahedral. If I can spell tetrahedral. And when we looked up on our chart, our tetrahedral bond angle was 109.5. So if we look at that, our bond angle is 109.5 degrees. Okay, so we can figure out the geometry, we can figure out the bond angle, we can figure out the electron geometry and the molecular geometry. The electron and the molecular geometry are not necessarily the same. They do tend to be different sometimes. Okay, So the next thing to do is figure out whether this is going to be polar or not. To determine this, we look at the bonds and we look at the shape of the molecule. So let's redraw that molecule and we'll redraw the dipoles. So if we look at carbon and hydrogen, carbon has an electronegativity of 2.55. And you can look it up on your electronegativity chart. I just have it memorized. Hydrogen has electronegativity of 2.20. So if we get the difference of that, which means we're going to subtract, we get a difference of about 0.35. Now, if you remember, everything was nonpolar if it was less than about 0.4. So that's less than 0.4. So this is going to be nonpolar. Now, if you truly wanted to draw the dipoles in here, carbon is slightly more electronegative than hydrogen. So we would have dipoles going these ways. But these dipoles are fairly weak. And if you notice, geometrically, if I add up all these dipoles, I have these two that I add up, they cancel each other out. And if I have these two that I add up, they also cancel each other out. So because they cancel each other out over the molecule, over the whole geometry of the molecule, this molecule ends up being nonpolar. So if the dipoles cancel each other out, that molecule will be nonpolar. If the dipoles don't cancel out, the molecule ends up being polar. I should write this as nonpolar. Okay, so you need to start thinking three-dimensionally when we look at things. Okay, so dipoles, I want you to think of them as a vector. I know you don't really do vectors in math anymore. Some of you might have had physics. Vectors have both direction and they have magnitude. So magnitude is this strength that we did, and the direction are these arrows that we just drew in. Okay? So if we were to add up all these dipoles, they cancel out. And we would have a nonpolar molecule. Okay? So remember, if the dipoles cancel out, then we have a nonpolar molecule. If we don't cancel out the dipoles over the geometry of that whole molecule, then we have a polar molecule. Okay, if we have a big enough electronegativity difference. Now, let's see. I would like to scroll down. Okay, now we drew in the molecule of methane. Okay, we want to draw in the dipoles. Okay, so the shape, we've got four. We've got 1, 2, 3, 4 areas of electron geometry or electron density. So our electron geometry, if we look at our chart, we've got 4 areas. So our shape is going to be tetrahedral. And because there all bonding, they're all shared, our shape is going to be tetrahedral. So electron geometry is tetrahedral. Our molecular geometry is also tetrahedral because all of those bonds, all of those electrons are bonding. And because the dipoles all cancel out, this is going to be a non-polar molecule. And our bond angle here is going to be 109.5 degrees. Okay? And that is also found on this chart, our bond angle, 109.5. Okay? So you need to get yourself really familiar with this chart and what is going on. We're going to do a few more examples, so don't sweat it quite yet. Okay, so let's look at this. We have ammonia, so NH3. Let's draw this out. So nitrogen gives us 5 valence electrons. Hydrogen gives me 1 valence electron, but I've got 3 of them. So 5 plus 3 gives me 8 total valence electrons. Now the next thing to figure out, what is going to be in the middle? I hope you said nitrogen, because hydrogen cannot be in the middle. It just can't make any more than one bond. Okay, so I've got nitrogen bound to those 3 hydrogens. I've used up 1, 2, 3 3 pairs of electrons. So a pair is 2. So 3 times 2 is 6. So I've used up 6 electrons. Where am I going to put the last 2? Hopefully you said on the nitrogen, because if I put a lone pair on the nitrogen, that satisfies the octet of the nitrogen. Now remember, hydrogen's already satisfied because hydrogen can only take 2 electrons. So let's do our little counting. How many pairs of electrons are around that center atom of nitrogen? Let's count. We've got 1, 2, 3, 4 pairs. Okay? So if I have 4 pairs of electrons around the center atom, what is the electron? So I'm looking at the electron geometry. So I've got 4 pairs that are around that center atom that are there. So the electron geometry is going to be tetrahedral. Let's look at this other chart. It's a little bit more clear. So 4 pairs around that center atom, my electron pair geometry is going to be tetrahedral. So the geometry of this is tetrahedral. Now, the next thing I've got to figure out, how many are bonding pairs? Okay, so let's change my color here, make sure it's nice and bright. I've got 1, 2, 3 bonding pairs. I've got 1 non-bonding pair. Okay, so let's look at our chart again. I've got 3 bonding pairs, and the non-bonding pair is called a lone pair. So I've got 1 lone pair, so I'm going to have a trigonal pyramidal molecular geometry. So, oh wow. The name of the shape for that molecular geometry is trigonal pyramidal. Now, if I want to look at the bond angle, I'm going to want to look at this other chart. This other chart, notice I have 4 pairs of electrons, but 3 are bonding, 1 is not. 1 is a lone pair. I have my trigonal pyramidal with a bond angle of about 107.3. So my bond angle here is going to be about 107.3. Now you're like, wait a second. Let's take a look at this chart. Notice this lone pair takes up a little bit more room than a bonding pair. I don't have a second nucleus for those electrons to spread out around for those. So those electrons are going to kind of bunch up and spread out because they're going to repel each other a little bit. So because they repel each other a little bit, they push down on the rest of the bonding pairs and kind of smush that bond angle a little bit. Okay? All right. Let's do some more. So non-bonding electron pairs take up a little bit more space than bonding electron pairs. So that bond angle comes out to be about 11.3 degrees. They smush it down. Now the next thing to do is figure out, is that polar or nonpolar? Now let's look at the electronegativities here. So nitrogen has electronegativity of about, let's see, it is about 3.05 if I remember correctly. Yep, 3.04. And hydrogen is about 2.2. So the difference here is, let's see, 0.84. That is definitely bigger than 0.4. So that would give us polarity. Let's see if these dipoles cancel out. Now notice in this is kind of a pyramid. It doesn't lay flat. So if I have a dipole that's pointing up this way, and another dipole that's pointing up this way, and another dipole that's pointing up this way, those dipoles are all pointing up slightly. They do not cancel out because this molecule is not flat. Let's see if we can see it a little bit better on this diagram. Do you see how it's not flat? And if we have these all pointing up, those do not cancel out because they're all pointing up. So this molecule is going to be polar. It will be polar. So we will have more electrons on this end. That nitrogen, especially with that lone pair here, will be very electronegative. And we will have partial positive charges on the hydrogen ends. So we will have a negative side to this molecule, and we will have a positive side to this molecule. Okay? I like to pretend that these dipoles are acting like tiny spaceships, pushing and pulling on that center atom. If that center atom moves, then that molecule is polar. Okay? It's kind of a tug of war. If that center atom does not move, then that molecule is nonpolar. It's as simple as that. So why do you think I have a picture of the Millennium Falcon here? I like to pretend that these dipoles are kind of spaceships like the Millennium Falcon pushing and pulling on that center atom. So it's a good visualization to have. Okay, so let's look at water. Okay, so if I look at water, oxygen gives me 6 valence electrons, hydrogen gives me 1 valence electron, and I've got 2, so I've got a grand total of 8 valence electrons. Okay, now the next thing we've got to decide is what's going to be in the center. Hopefully you said oxygen. So I'm going to put oxygen in the center here. Okay, hopefully my computer will stop having to think. Sorry about this. Okay. So hopefully you put oxygen here in the middle. Oh, good heavens. Okay, so that used up to 4 of my electrons. Okay, that used up 4. Now, hydrogen is already satisfied, but oxygen only has 4 electrons, so it needs 4 more. So I'm going to put 4 more there to satisfy oxygen's octet. That has made me use 2, 4, 6, 8 electrons. So 2 here, 2 here, 2 here, and 2 here. So I've used all 8. So everyone's satisfied with their octets. I have used up all 8 of my electrons. Okay, so let's now do our inventory. How many electron pairs or regions do I have around that center atom? I have 1, 2, 3, 4. I have 4 regions. Okay, so if I have 4 regions around that center atom, my electron geometry, let's see, 4 regions around that center atom, my electron geometry is going to be tetrahedral. Okay, so let's use this chart really quick here. 4 regions, my electron geometry is going to be tetrahedral. Now, hopefully you also noticed that I had 2 lone pairs here. So that means my molecular geometry is going to be bent. Okay, so my electron geometry is tetrahedral. How many of these regions are bonding? Well, this one is, and this one is. So I have 2 that are bonding. How many are non-bonding or lone pairs? This one is, and this one is. So I have 2 that are non-bonding. Okay, so if I look at my chart, we said that our molecular shape, the molecular shape would be bent. Now, if I look at my other chart to figure out the bond angle here, okay, so 4 electron areas, 2 are bonding, 2 are not. I have a bent geometry. I have a bond angle of 104 because once again, these 2 lone pair areas are going to take up more space than a bonding pair. So it's going to smush down on that angle a little bit more. So I have what's called a bent geometry. Okay, so our predicted bond angle is going to be 104.5 degrees. Okay, now let's look at that geometry here. If I really draw it the way it is, with this lone pair out here, and this lone pair out here, and this lone pair out here, now my electronegativity of oxygen is 3.44. And my electronegativity of hydrogen is 2.20. So my difference here is 1.24. It's very high, very, very high. So let's see. Oxygen is definitely going to be more negative. So do those dipoles cancel out? No. We're going to end up with one large dipole that goes through the molecule, kind of like that. Okay, we will have a large dipole that goes through that. So that molecule is very negative on the oxygen end and very positive on the hydrogen ends, just because of that huge difference in electronegativity. So water is very polar, very, very polar. Okay, let's try some of these together. Boron. Let's do boron. Okay, so if we look up boron, boron has 3 valence electrons. Fluorine has 7 valence electrons, and we've got 3 of them. So when we add all of that together, Let's see, 3 plus 21 gives us 24. Now remember, boron is an exception to the octet rule. Because boron only has 3 valence electrons to share, it can only make 3 bonds. Because remember, these covalent bonds are sharing, so it can only share 3. So let's look at this. If I look at boron and fluorine, so I've made my 3 bonds. I've used up 6 electrons. I still have 18 to use. Fluorine only has 2, and it wants a full octet. So I'm going to need to put 6 electrons on each fluorine to satisfy the octet for fluorine. Now the question is, I've got satisfied fluorine's octets. I've used up all 3 of boron's electrons, so that's all boron can do. Have I used up all 24 of my electrons? Let's count. Let's do another color. So 2, 4, 6, 8, 2, 4, 6, 8, that's 16, 2, 4, 6, 8. 3 times 8 is 24. So yeah, I have. So the next thing we've got to do is we've got to look at how many areas of electron density I have around that center atom. I've got 3 electron areas, and 3 are bonding. So let's look at that on our chart. So I've got 3 areas, and they're all bonding, they're all shared. So I will have a trigonal planar geometry with a bond angle of 120. Okay, so let's go and answer our questions over here. Our shape here is going to be trigonal planar. And now it's called trigonal planar because it's all within a plane. It's flat. Okay, it is totally flat. Our bond angle is going to be 120 degrees. Now think about this, our polarity. Let's look at our electronegativities. Now if I look at fluorine, if I look at fluorine, oh my, it's not letting me write. So if I look at fluorine, I've got an electronegativity of 3.98. And if I look at bromine, I've got an electronegativity of 2.04, which gives me a difference of 1.94, which technically would give us an ionic bond, but we have 2 nonmetals. So this will be covalent. This will be one of our ones that does go against the rule of thumb. So if I look at this, fluorine is going to be way more electronegative, just way more electronegative. So we will have dipoles on all of the fluorines like this. Now, if they're all 120 degrees apart from each other, that means they're all equal distant from each other. So I want you to think of this as an equilateral triangle. If they're all equal distant from each other and they're all the same strength, right? These are all going to be the same strength, and they're all equal distant from each other. Don't they cancel each other out? So if these dipoles cancel out, what happens to the polarity? The polarity cancels. So this molecule ends up being non-polar. Okay? So let's look at Let's look at oxygen dichloride. So oxygen has 6 valence electrons. Chlorine has 7 valence electrons, and I've got 2 of them. So 14 plus 6 will give me 20. Oxygen's going to be in the middle. So if I put oxygen in the middle, let's see, I've already got 2 for this chlorine, so I'm going to need 6 more to fill its octet. I've got 2 for this chlorine, so I'm going to need 6 more to fill its octet. And oxygen here has 2 on this side as well, so it's going to need 4 more to have its octet. Okay, so have I used all 20 of my electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yep. Okay, now let's look at that center atom really quick. So on that center atom, I've got 2 bonding and I've got 2 non-bonding. Okay, so let's look at our shape. Okay, 2 bonding and 2 non-bonding. So if I have 4 electron pairs, 2 that are bonding and 2 are not bonding, hopefully you remember from water that it will be a bent geometry. Okay. Why won't this let me move? It won't let me move. Okay. So this will be a bent geometry with a bond angle of about 104.5. Oops, I want to put a decimal. 104.5 degrees. Now, polarity. Let's look at the polarity. Oxygen has an electronegativity of about 3.44. Chlorine has an electronegativity of about 3.16. So our difference here is about 0.28. So in all reality, it is not bigger than 0.4. So we do not have enough of electronegativity difference, even though we have a bond angle like this. The electronegativity difference is not big enough to be polar. So this is going to be nonpolar. Okay? All right. Let's do another. Beryllium fluoride. So beryllium does not follow the octet rule either. Beryllium only has 2 valence electrons, and it can only share 2 electrons because that's all it has in its valence shell. Fluorine has 7 valence electrons, and I've got 2 of them, so altogether 2 plus 14 will give me 16. So here we go. Beryllium, fluorine. Now beryllium can only make 2 bonds, and it's already done that. Fluorine has 2 electrons, so it needs 6 more to fill its octet. So I'm going to put in 6 more with lone pairs, 3 lone pairs each. Let's see, how many electrons have I used? I've used 2, 4, 6, 8, 10, 12, 14, 16. I've used all 16. My fluorine's octets are full. Beryllium is doing all it can. So how many areas of electron density do I have around that center atom? I only have 2. So if I look at this, I only have 2. If I have 2 areas and they're both bonding, I'm going to have a linear geometry with a bond angle of 180. Okay? So 2 pairs, they're both being used in bonds. My linear geometry is going to have a line of 180. Okay? So shape is going to be linear. And my bond angle is going to be 180 degrees. Okay? All right. Let's do some more. Now, polarity. Let's look at this. Fluorine is going to be heck of a lot more negative or electronegative than beryllium. Fluorine is 3.98, and beryllium is 1.57. So let's see, 1, 4, 2. That is really a huge electronegativity difference, to the point that we would expect it to be ionic. And yeah, it pretty much is ionic. Okay, now notice these dipoles are exactly the same size. They're both 2.1, and they're exactly going opposite of each other. So geometrically, if I have something pulling opposite the same force, that means that the forces cancel. So our polarity cancels. So this ends up being a nonpolar molecule. Okay? All right. Carbon tetrafluoride. Let's get this next one. Carbon tetrachloride, we've got carbon, which gives us 4 valence electrons, and we've got fluorine, which gives me 7 valence electrons, and I've got 4 of them. So 4 times 7 is 28, plus 4 gives me 32 valence electrons I've got to place. Now, carbon's going to be the one in the center. Hopefully you guessed that. Okay, carbon, let's look at carbon. We've already got 2, 4, 6, 8 electrons around there. So carbon's octet's already satisfied. Fluorine, we've got 2 electrons on each of the fluorines, so they need 6 more to satisfy their octets. So let's satisfy fluorine's octets by giving them 3 lone pairs each, or 6 electrons. Okay, have I used up all 32 of my electrons? Now, if I look at each of these fluorines, they're all the same. So let's count one up, and then we'll multiply it by 4. So 1, 2, 3, 4 pairs. 4 times 2 is 8. And I've got 4 of those same things. So 8 times 4 is 32. I've used all 32. Now let's look at that center atom. I've got 4 areas of electrons, and they're all bonding. So if I look at my chart, I've got 4 areas right here, and they're all bonding. So I'm going to have a tetrahedral arrangement. Okay, so the shape here is going to be tetrahedral. The bond angle on a tetrahedral is going to be 109.5 degrees. Now, hopefully this reminds you of methane. It should remind you of methane. I've got dipoles going out to the fluorines, because fluorine is way more electronegative than carbon. Let's do the math. Fluorine has an electronegativity of 3.98, and carbon has an electronegativity of 2.55. So if we do the difference here, it's pretty big. It's a pretty big electronegativity difference. But if you look at these dipoles, they all cancel each other out. They all are pulling the opposite ways. So when we look over the whole molecule, all those dipoles cancel each other out. So this is non-polar. Okay, last but not least for this video, the ion of ammonium. Now, when I have a positive charge, I'm going to take away electrons. If I have a negative charge, I'm going to add electrons based on the number of the charge. So let's show you how that's done. Okay, based on the number of that charge. So nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, and I've got 4 of them, right? But I've got this positive 1 charge. So I'm going to take away 1 electron. So 5 plus 4 is 9, minus 1 gives me 8 valence electrons that I'm going to place. Okay, so hopefully you realize that nitrogen is going to be the center. We're going to put single bonds around each of those 4 hydrogens. Now, in terms of what I have, I've used, let's change our color really quick.